This is our split line bandsaw project completed by Settineri, Derek Steele, Jonathan Fiscus, and Tayler Schwabenbauer. U.S. Braun Foundry and Machining Incorporated currently produces a variety of large bushings for mining and bridge applications. Bushings require a slitting operation to relieve internal stress. It is done by splitting on a manual mill by a slitting saw or an end mill. The current method is not very efficient and it takes a long time to complete. Therefore, we need to design a bandsaw that will cut large bronze alloy split bushings autonomously, accurately, efficiently, and safely. The bushings in question are shown here. The bushing on the left is the initial bushing, and the bushing on the right is what we need to be able to cut into. So therefore, we're going to need a large saw that's going to be able to cut through something so large. We took a trip to U.S. Braun to see the bandsaws that are already in action and to get a good idea of the size of the bushings that we're going to need. So off to the drawing board we went, where we were able to break the system down into 5 separate subsystems: the superstructure, energy conversion, tensioning, feeding, and control. We were able to complete the superstructure design and get the free body diagram completed. This was the first stepping stone in being able to complete the rest of the subsystems. The next subsystem that we decided to tackle was the blade tensioning system. We were able to work with Parker Hannifin Corporation, where we picked out a good piston-driven tensioning system. To complete the tensioning system, we had to go through a frictional analysis between the blade and the wheels. Once the blade is in tension and in action, we had to do some friction testing to be sure that the blade is not going to slip on the wheels. After experimental analysis and getting data, we were able to decide on using a rubber tire with a coefficient of friction of 0.233 and a wraparound angle of 144 degrees. We then dove into the energy conversion subsystem. We then needed to do some technical analysis and calculations to be able to pick out an appropriate motor that will be able to drive our blade. We were able to pick out a 3-phase AC electric motor and a helical bevel gear reducer gearbox. When looking into the control systems, we were able to pick out a PID controller which keeps the blade at a constant speed despite the changes in the load. The limit switch will cause the saw to automatically retract at the end of the cut, and the second limit switch will turn the saw functions off when fully retracted. After completing the analysis of all the subsystems, we were able to come up with this final bandsaw design. We would like to give a big thank you to our sponsor, U.S. Braun Foundry and Machining Incorporated, and Penn State Barron faculty and our professors.